Swayam Prabha. Digital India. Educated India.
So, lecture number 23. So, in this lecture we will be more focused towards polymer matrix and nano composites. So, basically what are we trying to focus is we are trying to focus on nano materials getting integrated into the polymer matrix for producing a composite. So, when we were talking about forms, that is fiber forms or forms which are getting reinforced, we were looking into which are like fiber, we were looking into particulate, we are looking into whisker, and nano is one more particulate type wherein which the dimensions, one of the dimension will be in nanometer scale. So, why is that required? Because there are certain requirements wherein which we would like to add more interface in the material. So, when we add more interface in the material, fracture toughness increases in ceramic matrix composite. As far as polymer matrix composite is concerned, it enhances the toughness property as well as wear resistance property. People have added nano materials which are conducting inside it. So, this has led to conducting polymers. So, in this lecture we will have the following content. So, it will be polymer composites and the factors affecting their property, nano composites and their fillers. Synthesis of nano composite, I have put in 4 processing routes, then advantage of nano composites, applications, and finally we will have conclusions. So, factors affecting the properties of a polymer matrix composite is more towards interfacial adhesion. So, interfacial adhesion has to be very strong, let it be a fiber, let it be a particulate, or let it be nano materials. So, the interfacial factor, that means the adhesion factor should be very strong. The shape and the orientation plays a very important role of the dispersed phase. For example, when we talk about fiber, we talk about orientation of the fiber 0 degrees, 45 degrees, 90 degrees and the orientation which is made so that we get a required output. So, when we talk about shape and orientation of particulates, the spherical nature or the sphericity, cubic, platelet size, that means to say we are talking about the aspect ratio, it can be regular or it can be irregular geometries can be thought of. The shape and the orientation of the dispersed phase inclusion plays a very important role. The last one is going to be the property of the matrix. So, the property of the matrix also plays an important role because it has to give enough of space for a particulate to go sit there properly to meet out the requirements. So, here when the properties of the matrix we put casting, easy processability, for example, all thermosets are easy to process, thermoplastic are difficult to process, good chemical resistance, low specific gravity, all those things are properties of the matrix which are very important factor while deciding polymer matrix nano composites for required application. On the other hand, low strength, low modulus and low operating temperature limits the usage of a particular polymer. So, based upon the requirement, we look into all those properties and decide a polymer whether it has to be a thermoset, whether it has to be a thermoplast or it has to be an elastomer. When we talk about matrix, so you have thermoplastic polymers, you have thermosetting polymers, you have elastomers and their blends. Today we have matrices wherein which a thermoset is mixed with thermoplast. A thermoset is mixed with elastomer to meet out requirements. So, when you talk about thermoplastic polymers consist of a linear or a branched chain molecule having strong intramolecular bond, but weak intermolecular bond. Intra and inter, please have a note of it. So, intra is within the same and inter is between two different particles. Reshaped by application of heat and pressure is a very common feature of thermoplastic polymers. The example for thermoplastic polymers we have seen enough. So, I have just put down the list. It is PE, PP, polystyrene, polycarbonate, and so on and so forth. When you look into thermoset polymer, they have cross-linked or network structure with covalent bond with all molecules. They do not soften, but they directly decompose with heat. Once solidified, the cross-link process, they cannot be reshaped. So, the examples are polyester, epoxy, phenolic, ureas and silicone are some of the examples of thermoset polymer. When we talk about the composite, so you can see that you have unreinforced polymer, which is the bend displacement. We are looking into force versus bend displacement, and then the next one is we are looking at fiber reinforced composite, and then the last one what we are seeing is particulate reinforced composites. In particulate reinforced composites, you see there is a gradual fall of the force. So, what are the advantage of polymer matrix composite? It has a very high E/R ratio. So, R is the density, or it can be considered as rho. You can make it as rho. Okay. It is rho. E/rho is very important. So, you can see polymers fall in this region, polymer matrix composites fall in this region, ceramics much higher, and metal alloys fall in this region. So, this makes polymer matrix composite more prominent for applications where weight is an important factor. So, if you see metal matrix composite, in metal matrix composite it increases creep resistance. So, you can see a whisker reinforced, this is a alumina whisker reinforced SiC, you can see the creep resistance behavior. This is a typical aluminum alloy 6061's response. So, when you look at nano composite, these are the classifications. The nano composite, it can be polymer based composite. Due to small size of the nanoparticles of the structural unit and high surface area to volume ratio, this we are talking about the nano. So, nano materials will have a very large surface area, but a very small volume. So, S by V. So, S is large and volume is small. So, here what happens is we do not talk about gravitational force, we talk about van der Waals bond, we talk about surface tension. All these small surface phenomena get into action and they try to dictate the process. So, gravity is no more important when we talk about nano, density is no more important when we talk about nano. We talk more in terms of surface to volume ratio because the signs changes. So, due to small size of the structural units and high surface to volume ratio, these nano composites, these are finding out, these nanoparticles included in nano composites are finding large utilization. So, when we talk about shape, these are various shapes which I have given. Spherical particles will have 3 by R, the fibrous particle will have 2 by L plus 2 by R, the layered matrix will have 2 by T plus 4 by L. So, here R, L and T represents the radius, length and the thickness respectively. Note, the surface energy increases as we move macro to nano. So, if we go to macro, the surface area becomes, if you assume the surface area is the same, but volume increases. So, now you see the gravitational force starts playing important role. So, when you go towards nano, the surface energy, the S by V ratio plays a very, very important role. When you talk about here, it is non-polymer based and a small amount of 5% of nano filler loading resulting in a pronounced improvement in the thermal and mechanical properties. So, when we are talking about fiber reinforcement, we talk about 30%, 40%, and when you do automatic, we talk about 60% and 70%. But when we work on this nano composite, adding 5% nano fillers into the matrix itself brings in a drastic improvement in thermal and mechanical properties. The filler can be 0D, that means to say a nanoparticle, can be 1D, which can be a nano wire or a nano tube, can be 2D, thin film coating on quantum wells, or 3D, which is embedded network or copolymers. These are some of the fillers which are possible by nanomaterials which are getting integrated into the composite. Okay. So, what is the processing difficulty with this nano composite? Nanoparticles have large amount of surface charges. So, moment you have large amount of surface charges, they quickly get agglomerated. Moment it gets agglomerated, then the functional property is not uniformly distributed all across the matrix. So, you will have chunks of nanoparticles loaded at few spots, and some area it will be exclusively polymers. So, here in order to break the agglomeration, we always try to functionally coat the nanoparticle, so that we play with the charges, they always stay little far away and then they do not agglomerate. This is a huge challenge. See, for example, when you have two huge challenges, one is agglomeration, two, the density. Nanoparticles are always very light. So, when you try to disperse it in a polymer matrix, they will always try to come to the top and they will try to stand there and get frozen. So, in order to have a uniform distribution, we have to think of novel mechanisms wherein which these particles enter into the polymer and get dispersed, then it gets cured. So, these two are the major challenges. So, this is what is a nano, this is a cauliflower structure which is there of nanoparticles. These are small nanoparticles which are dispersed in a polymer, and here you can see fiber, nanofibers which are dispersed in a polymer, and this is a CNT which is dispersed in a polymer. CNT is carbon nanotubes, and you can have single wall, multi wall, so you can get it done. So, in nano composites, very high surface area to volume ratio in nanostructures are there. The nano composites provides a very large interface area between the constituent and the intermixed phase. So, the interfacial area is more. Moment the interfacial area is more, when the crack grows, it gets arrested very fast. It allows significant property improvement with a very low loading at very low loading levels, because the density is low. Second, you will have more amount of particles, individual particles present when you try to weigh it. So, you will see lot amount of particles present even at a very low loading. So, traditionally microparticles additives require a much higher loading levels as compared to that of nanoparticles. This controls the degree of interaction between the filler and the matrix, thus influencing the property. It alters the chemistry, the polymer chain mobility, degree of cure and the crystallinity, etc. All these things are changed because of adding this nanoparticles inside a polymer. So, that is nothing but the nano composite what we make. The surface and the interfacial properties, example adhesion and friction forces becomes very critical as the material is very small. I have discussed this point. High surface area materials have application in energy storage, catalysis, battery and capacitor elements, gas separation, filtering, biochemical separations, etc. These are the areas where today nano composite, polymer matrix nano composite are used exhaustively. So, for energy storage, catalysis reaction in chemistry what we do, battery and capacitor elements for storing charges. Today we talk about supercapacitors, wherein which within very short period of time it stores and it discharges very slowly. Then gas separation, people are talking about for water filtration, they are trying to have a polymer matrix composite made, and they have functionalized CNT, and then they have dispersed it inside a polymer matrix. These are CNTs which are functionalized. So, they are dispersed in a matrix. Now, what they do is they try to make small holes, and through these holes they try to pass gases, and these gases are used for separation of and then this functionalized CNT might attract the gas elements all along the way, and it releases whatever is in the pure form. So, water filtering is also done in a very similar way to get the required output. So, if you look at it, the surface volume atomic ratio to cubic side. So, you can see that there is a decrease in the trend and there is a increase in the trend. So, this trend is move towards total number of atoms present, and this is surface to volume atom ratio percentage. You can see it decreases with respect to cube size, which is all in nanometers. What is the unique nature of the filler which we use? It is small in size. Very small nanoparticles do not scatter light significantly, possibly to make the composite with an which alters electrical and mechanical properties that retains optical clarity. So, what we are trying to tell is, we are trying to say electrical property and mechanical property can be changed by retaining the optical clarity. That means to say you will have a transparent material. So, transparent polymer which will be used for vision application, but it will also try to become electrically and mechanically stronger. Do not create large stress concentration. So, do not compromise on the ductility of the polymer. So, the sizes are very small. So, to a large extent ductility sacrifice is not there. So, leads to a unique property of the particle by themselves, which is single wall nanotubes are essentially molecules free from defects, having modulus as high as 1 terapascal, the strength as high as 500 gigapascal, which is very difficult to get in a single material, which is got in single wall nanotubes. It leads to exceptional large interface area in the composite. The interface controls the degree of interaction between the filler, polymer and the control properties. These are some of the unique properties which we get by using this nanoparticles while making composites. In the interfacial regions, this is a region beginning at a point in the fiber at which the properties differ from those of the bulk filler and ends at the point in a matrix at which the property becomes equal to those of the matrix. Okay. So, this is very important. So, the property differs from those of the bulk filler and ends at the point in a matrix at which the property becomes equal to that of the matrix. So, you will have a very smooth interfacial changes, that is what we are trying to say. It can be a region that alters chemistry, polymer chain mobility and alters degree of cure and crystallinity. The interfacial size can vary from 2 nanometer can go up to 50 nanometer. The biggest challenge for us is to visualize this 2 nanometer. It cannot be done by optical, it cannot be, majority of the time it can also be not done by electron. So, we always go for transmission electron. So, here I mean to say scanning electron, and this is optical microscope, scanning electron microscope and transmission electron microscope. So, if you want to see the agglomeration and other things, so it is very difficult to do in scanning electron. So, we always go for transmission electron microscope. So, here we try to see very small particles and then we also try to look at their crystallinity, how is it, we get to see the distribution. So, the advantage, electrical property can be changed by adding CNT, the mechanical property can be changed because you have lot amount of toughness, and the elastic modulus and the strength of the vinyl ester component can be changed by adding alumina particles of 40 nanometer size. This also can be done. So, mechanical, electrical properties can be changed by adding these fillers. So, the factors influence the microstructure and the properties of a nano composite, the surface modification of the filler and its interaction with the polymer, the filler volume fraction, the aspect ratio of the filler and the filler alignment, whether it is oriented in one direction or it is randomly distributed. These are factors which tries to influence the nano composite properties. The surface modification of the filler, that is what I said, functionalization of the, so if this is a, so here you will add some charge particles and these charge particles try to change the interaction with the polymer. The number of particles present is the volume fraction, aspect ratio. So, here S by V, aspect ratio is very, very important. The filler alignment, it can be random alignment or it can be oriented in one direction. So, what are the most common synthesis route for nano composite? These are the 4 or 5 very common preparation route for nano composite: solution casting, melt blending, in situ polymerization, electrospinning and electrodeposition. In situ polymerization, when you do polymerization, the particles gets generated of its own. So, these are nano in shape, so it gets dispersed. In solution casting, a polymer, a solution and a nano reinforcement are combined, thoroughly mixed by ultrasonification. So, what is ultrasonification? We use ultrasonic agitator, ultrasonic tool, wherein which we fill the polymer. So, the tool is there. So, it tries to vibrate in 21 kilohertz with a small amplitude and creates lot of cavities. So, these cavity bubbles keep moving towards the top and dispersing. So, where at this we will try to disperse the nanoparticles. And there are several tricks. For example, when you do epoxy, the temperature might go very high. So, we put it in an ice bath. So, this is an ice bath we put. So, in order to maintain the temperature of the polymer, we put it in an ice bath, right. So, it can be done. People used to disperse polyester, epoxy resin, and all the liquid resins can be dispersed. For example, elastomers. You can also choose elastomers and disperse nanoparticles like this. So, here ultrasonification is very important because that creates cavitation. When this cavitation bubble bursts, then there is a space for a nanoparticle to get inside and it gets properly mixed all around. So, thoroughly mixed by an ultrasonification, and the solution or solvent is allowed to evaporate, leaving behind the nanoparticles typically as a thin film, right. So, ultrasonification, and the solutions or solvent is allowed to evaporate, leaving alone the thin. So, all these nanoparticles will form a thin film, or it can be uniformly dispersed. Now, you pour it inside a dye, you get a nano composite. The solvent or the solution chosen should completely dissolve, and the polymer as well as disperse the nanoparticles. The solution solvent used with the help in the mobility of the polymer chain, which in turn helps in intercalcination of the polymer chain with a layered nano reinforcement, leads to a nano composite. So, you can do like this, or you can try to have polymer which is blunt in a solvent, nanoparticles blunt in a solvent, both these solvents mixed together, evaporated, form a thin film, get a nano composite. Okay. So, this is what it is. So, this is called as solution casting. So, the major advantage is going to be the greater the film thickness, uniformity will be there. Wide range of films can be made. The films that are gel and a pinhole free, the excellent flatness and dimension stabilities can be got. Isotropic property orientation, as film is not stretched during manufacturing, you get a very good isotropic orientation. Then absence of extrusion process lubricants, and then it is suitable. The suitability of the polymer solution casting is evaluated case by case basis according to the product formation. So, this is what is the solution casting. You see PU, it is getting formed. So, you heat it to a certain temperature, measure the stir the particle, then you nanosonicate it, then you add all the nanoparticles into it, then you stir it, and then you heat it. So, you allow all the solvents to evaporate, or you leave it as a polymer, so it gets uniformly dispersed. Then finally, you do degassing, and then from the degassing you try to pour it on a spin coating, and then it forms a small thin uniform layer. You can either do it in the spin coating machine, or if you want, you can even go ahead casting it. So, this is what it is. So, here a PU, then it is mixed with a solvent. So, you mix it here, then it is stirred. So, uniform dispersion, this is a stirring action. Stirring action is uniform dispersion of solvent and polymer, or polymer inside everything. Then you try to take the nano wall, whatever CNT or nano material, and then disperse it in a liquid. So, this liquid is again dispersed inside the polymer. So, it is sonicated for 15 minutes, and you say that 70% amplitude they have set. So, 70% of maybe 10 microns or 50 microns they do it, and then they try to vibrate it. then pour this solvent, then you allow it to cure, degas it, get it, and then this can be casted or it can be spin coated so that you get a thin film of whatever polymer you want. The manufacturing process advantage of polymer solution casting over the traditional film extrusion method is included. The processing happens at low temperature. It is valuable for thermally activated films or application incorporating temperature sensitive active ingredients. The ability to produce high temperature resistant films from non-thermoplastic but soluble raw materials can be done. Simplified incorporation of additives and fillers can be done in this. Quicker changeover for platforms which many part numbers that are differentiated based on the formulas can be done here. Single pass manufacturing of multi-layer films can be done. So, you can also make functionally graded materials also can be done. Every spin coat layer can have varying volume fractions and you can have a functionally graded material. Wider range of material choice with casting from either aqueous or solvent based solutions can be done. The basic material intended to use and numerous other considerations are specific benefits are realized for the following applications is acrylic and the other polymer films deliver superior optical properties and thickness uniform. When you talk about polyurethane film, improves mechanical properties such as elimination of pinholes or voids. Also ensures film uniformity, high optical clarity and production of thin films which can be easily customized with added functional layer and properties. The thermoset additive films where melt extrusion is not feasible, we try to do it. The thermal interfacial material, addition of more concentration thermally conductive fillers than the feasible of the melt extrusion process can be done here. Electroactive polymer films can also be made by this process. So, the melt blending is the other process. We take a polymer, we take a nano material, it is extruded, it is intensive mixing is happened, then it is pressing using a die and then you get a nano composite. In this method, the polymer mobility simply comes out from the thermal energy. So, this is melt blending process, a schematic diagram. So, here you try to take the polymer and then what you do is you try to extrude it at 240 degrees Celsius, 100 RPM, you try to do this and then you try to mix it up. You put it in a compression mold and then you try to press it at 240 degrees for 5 minutes and what you get is a thin film which is done by melt blending. So, this is a thermoplastic polymer which is taken, it is extruded and then you try to get it. Okay. There are twin screw extruders which are used wherein which you can even disperse solid nanoparticles and then you try to disperse it to get and it is it is like an injection molding machine. Twin screw extruders, injection molding, you directly inject it into a die to get the required part. Okay. So, this is a model of the experimental line for preparing PET functional foils, making a nano dispersion liquid by blend milling. So, here we make PET granulars via melt blending process and the preparation of the infrared shielding foil by adding a PET granule above. So, here you can see that. So, we make a powder, dispersion in a liquid, granules are made, these granules are rolled and then when you roll we try to add this, here we add nanoparticles, granules, nanoparticles is added, you roll and then you stretch it and then you get PET foils and then these foils are rolled up into this so that it can be sold at commercial applications. So, what is the advantage here? Naturally, the advantage is going to be it is going to have higher strength and the number of defects are going to be less in melt blending. So, shows a higher gas barrier performance compared to that of solution casting. Here formed exfoliated nanostructure while those prepared with the solution exhibits intercalcinated structures only. So, here it is much more stronger than the solution casting. The melt blending film shows higher creep resistance than the intercalcinated ones. The nano composite films show superior physical properties and can be prepared with NB method, or EC and environmental friendly techniques can be used. So, melt blending method is always beneficial than the solution casting method. The next topic of discussion is going to be in situ polymerization. So, in situ means I think it is getting developed while the process is going on by adding two independent elements, you add together and then it mixes, it tries to generate a polymer nano composite. So, in situ polymerization, as you all know, lot of mers joining together to form a polymer. So, in situ polymerization, in this there are two important discussions to be carried out. This is with regard to the nano material which is getting reinforced inside the polymer material. There are two processes, one is called as intercalcination, the other one is called as exfoliation. As you know, in nano composites they are charged. There is a lot of charge around the nano composite, it is going to create agglomeration. So, I have to separate these nanoparticles. So, basically I try to do functionalization, and in the same thing a nanoparticle can have multiple layers and each layer will be a nanometer. So, I want to separate these layers one from each other such that the agglomeration does not happen. For this what we go ahead is we do this intercalcination and exfoliation. Intercalcination is the reversible process, like reversible inclusion or insertion of molecule or ion into the material with layered structure. So, this is very clear. Intercalcination and exfoliation can happen only with layered nanoparticles or layered nanomaterials. So, what I try to do here is I try to separate these layers. For example, I have several layers of some material stacked to each other. So, what I do is I try to put spacer in between. So, what has happened? I have now separated the layers. So, that is what is happening in intercalcination. So, I try to add a material such that this material is getting included into the nano layers and it separates out nano layers. The intercalcination expands the van der Waals gap. So, as I told you, in nanomaterial, all with the van der Waals forces, surface tension, all these things play a very important role. The van der Waals gap between the sheets which requires energy, what we do is we try to push in this material, this ion or a molecule inside such that it separates out. Usually this energy is supplied by charge transfer between the guest and the host solid. So, guest these are the guests, these are the host solids. I try to have separations such that you can now get layers of nano structure. Exfoliation is nothing but an extreme case of intercalcination. In intercalcination, if you still see that there is an attachment between the layers. Now, I get layer by layer by layer material. So, all these layers are in nanometer dimensions, one of the dimensions are in nanometer. So, exfoliation, an extreme case of intercalcination where the complete separation of the layer of the material happens. So, how do you do it? After you put this inside, still there will be sticking. So, I aggressively try to break the bond. So, the typical aggressive conditions are required to remove the highly polar solvent and the aggressive reagents. They react and then this fellow gets disintegrated such that I get layer by layer by layer. Now, each layer is of nanomaterial dimension. So, what I explained you is given in clear picture here. So, these are the layers. Okay. So, it is layered structure with gallery. So, now in this layer it is all attached to each other, just for schematic representation we are given the spacing. Now, what I do is intercalcination, something flows in between and it tries to separate out a distance, right. In exfoliation what happens, this distance is further enhanced and we separate out layer by layer by layer. So, in situ polymerization method. So, in situ polymerization method was first reported by Toyota researchers from the synthesis of a polyamide nanocomposite that led to the exponential growth in the nanocomposite research. For generation of polymer nanocomposite, by this method, a layered silicate mineral is swollen in a monomer. So, what have you done? The layered silicate is inserted, or it's dissolved, or it's put inside a liquid. So, this liquid will try to swell, or it will try to separate out. So, after swelling, the polymerization of the monomer is initiated. So, now it is swelled. So, once moved apart, there is enough space for polymer, whatever it is, to happen. As monomers is present in and out of the filler interlayer, the generated structure is exfoliated or significantly intercalcinated, removed a layer out, and the polymerization happens. A rate or the mechanism of polymerization in and out of the filler interlayer may be different. Therefore, it is important to control the inter-gallery or the extra-gallery polymerization reaction for getting uniform reaction. So, what I am trying to say is, I am trying to say this is separated by a monomer, and after this is added to, or in this what happens, you try to have a reaction to form in situ polymerization of generating polyamide nanocomposite. If you look at the schematic diagram, so you can see in situ polymerization, I add a monomer, I add graphene, CNT, or inorganic filler, whatever it is, which has a layered structure. So, then it is put together in a solvent. Now, in a solvent, what we do is, you have to somehow push the layer in between. So, if you have to push the layer in between, you have to aggressively create a space and push inside. So, this can be done by ultrasonification. In ultrasonification process, what we do is, we try to vibrate the solvent at 21 kilohertz. It creates cavity, small bubbles. These cavities are broken, or it is blast, and then when it is blast, it creates so much of pressure there. So, it is easy for a material to go inside, or it can get inside some material without any problem. So, that is why we always go for ultrasonification. Ultrasonification is always used for homogenizing the reinforcement in a viscous material. We go for ultrasonification. If the viscosity is slightly low, then we also go for magnetic stirring. So, this too is done only to get uniform dispersal. Then afterwards, the mixture, that is the swelling of the filling happens, and then we add initiators. These initiators are added for initiating the polymerization. Then I have to accelerate my polymerization. So, I try to give heat rather than giving a heat by a laser and other things, which is for a spot. We always try to give for radiations. So, this radiation can be UV, can be infrared, such that the polymerization happens. The in situ polymerization is this. So, here what we do is, we are trying to work on thermoset polymer matrix composite. So, you have a solvent, mixture is there, polymerization can happen. After this polymerization, surfactant SDS under continuous stirring happens, and then you form micro emulsions. Okay. So, by this way we try to form, this is micro emulsion polymerization. By this way we try to form in situ polymerizations. Since thermosets are liquid in nature, this process is very easy. To a large extent, it is easy to get uniform homogenization of the reinforcement in a polymer. So, the schematic diagram I have just put here. So, inorganic filler is used, and then we add polymer to it. We allow it to swell. So, it is swelled. So, this monomer goes inside. So, polymerization happens. I apply heat, heat in the form of light I apply. So, intercalcination of the platelets happens, and then this is a polymer which is formed. The monomer is converted into a polymer, and that is how you get a polymer nanocomposite in the in situ polymerization process. Now, I think it should be very clear for you. So, I have put one more example. So, in this example you can see the in situ micro emulsion. What is this micro emulsion? This micro emulsion, what we were talking about, micro emulsion polymerization, right. The same thing we are trying to take, in situ micro emulsion polymerization technique for polystyrene and graphene. What is graphene? Graphene is another form of a carbon. So, we are trying to, graphene is being pushed into polystyrene. So, maybe they wanted to have a conducting property, so they do it, or they would like to have a better fracture toughness property, they are doing it. So, there are several applications. So, EG is taken, so graphene is taken, and then these graphene are expanded, and moment it is expanded, they are expanded by applying very high temperature. By this, what we have is, we try to take a single layer of graphene. Now, the single layer of graphene at room temperature is dispersed in a water bath. So, what are you doing? You want to add something into the graphene layer, or if you want to delete something into the graphene layer, you can get it done. So, when you want to add, it is called as functionalization. When you want to remove certain things which you do not want, so then also we try to do this water. Water is something which is easy to handle, and it is low viscous. So, it can be easily mixed with graphene. So, when you want to mix with graphene, we always use a process called as ultrasonification. Ultrasonification process. So, in this process, we try to add some functional agents. Then at room temperature, the SDS. What are SDS? SDS are nothing but surfactants. You see that SDS, add surfactants under the continuous stirring. So, these surfactants are added, again it is getting functionalized. So, now you see uniformly it is all dispersed. Then at 0 degree Celsius, what we do is, we try to add styrene droplets, polystyrene. What you want is polystyrene. So, for styrene droplets are added. Then at 85 degrees Celsius, you again sonicate, you see that these polystyrene particles are formed, and this SDS is also added. So, they try to mix each other properly and try to get whatever is the output. So, now these are polystyrenes which are there. The polystyrene are made, and then we try to pour it inside a die or extrude it in a strip, whatever it is. We try to get the polymer nano composite, that is polystyrene graphene impregnated polymer nano composite for various applications. You can see the red dots are polymers, polystyrene, and the functional parts are also mixed. So, you get the, and graphene is also mixed. So, you get a host matrix, and then you get the final output. The next interesting process is electrospinning. What is electrospinning? Electrospinning, what we do is, we try to generate nano fibers. How do we generate nano fibers? We try to take the liquid, what you want to convert it into a fiber. So, in this syringe, what we do is, we apply pressure here, and slowly the liquid which is here is through this syringe is try to flow out. And simultaneously what I do is, I try to create an ambience where in which there is a very high potential. So, when the liquid comes out and when there is a very high potential done, it try to generate nano fibers. These nano fibers are stuck on or are grown on top of a rotating mandrel or a flat mandrel. So, what is happening is, it gets uniformly rotated. So, all around the mandrel you will have now nano fibers which are getting impregnated or which are getting formed, which is just gets stuck, physical sticking happens. Okay. So, this is what is electrospinning process. It's a very interesting process. Now, lot of things are getting electrospun, and they get try to get the output. For example, today they make fibers. These fibers are used for water treatment. They have they functionalize these fibers with such an element or with such a functionalizing agent. It tries to attract arsenic, and it completely absorbs arsenic, and you get to a large extent you try to remove arsenic from the drinking water. So, for this we use this nanofibers, and this nanofibers are dispersed in a polymer. So, it is nothing but a polymer matrix nanofiber reinforced nano composite is there. So, this is having lot of role today. So, here in the schematic a standard horizontal, you can have this horizontal or you can have this vertical. Standard horizontal electrospinning setup is shown for at least a syringe pump. So, this is a syringe pump. So, through this syringe you have a pump which gives the pressure, so that it tries to eject out very small quantity of a polymer solution. Okay. So, this is at a very high voltage is applied at the electrode sources, and then it is, and the collector source a very high potential is applied, and then you try to generate this nanofibers. Out of this syringe, out of the syringe you will have the needle tip, you can see there is a Taylor cone which is formed, and this Taylor cone will help in making nanofibers. So, the entire process goes in making this Taylor cone, and this Taylor cone formation is a big challenge. Moment it is formed, then the fiber is a continuous process, it produces lot of things. So, in electrospinning can be used to prepare fine composite nanofibers with a diameter from nanometer to micrometer range. You can have the diameter and the length can be long. The preparation of the precursor mixture involves dissolving the polymer matrix and the graphene in the solvent. So, we mix it and then put it in the electrospin. The mixture is then electrospun. So, what are we trying to do? We are trying to mix polymer, we are trying to mix graphene, and then we are trying to eject it out. Okay. So, the mixture is then electrospun by applying a very high voltage of 5 to 20 kilovolt on the syringe needle. During the typical process, the polymer solution held by its surface tension. Please note, during the typical process, the polymer solution held by its surface tension at the end of the syringe needle is subjected to a very high voltage field, whereby a charge is induced on the liquid surface as a result of high voltage applied, and the mutual charge repulsion induces a force directly opposing to the surface tension. So, something pulls out and there is a resistance, something pulls out, and then you try to form a Taylor cone. Okay. So, here whereby a charge is induced on the liquid surface, what liquid comes out? What liquid comes out? There is a force which is given. So, this will try to restrict the flow as a result of the high voltage applied, and mutual charge repulsion induces a force directly opposite to the surface tension, and such high voltages forms a hemispherical surface at the tip of the needle, which is eventually elongated and forms a Taylor cone. There is a lot of science which goes by, for the formation of this Taylor cone. So, this is very important process, and here we try to mix it with the polymer and try to get the required output. When a critical voltage value is reached, the repulsive forces overcomes the surface tension of the solution, and the charge jet of the solution is eject out the tip of the Taylor cone itself. The high voltage application leads to the formation of ultra fine composite fibers with diameter micrometer range to nanometer range, while which are electrospun as a solvent evaporates when the jet is travelled through air, and then behind a polymer fiber on the collector is done. So, you can have a polymer fiber. So, it can be beautifully done. You can have a polymer fiber on a polymer matrix, and then you can spun everything, and then you can almost have one more polymer layer, then you can spin. So, what you have is you have functionally graded materials, or you can also have functionally controlled or tweaked materials. So, the voltage applied leads to the formation of ultra fine composite fibers with a diameter in a micrometer or nanometer range, and then when it is spun, if there are solvents, because these solvents are generally used for flowing. So, the solvent evaporates while it comes into the free air contact and leaves behind a polymer fiber on the collector. The electrospun fiber presents an interesting property as high surface volume to volume ratio, leading to low density, high pore volume, and outstanding mechanical strength can be brought in when you do electrospinning process and generate a polymer nano composite. However, the process parameters as well as the choice of the system includes the type and the molecular weight of the polymer, the polymer viscosity, solvent used, voltage applied, needle of the collector distance and the polymer flow rate often plays a crucial role in achieving the desired properties in the nanofiber composite procedure. So, this is another process which is electrodeposition. So, in electrodeposition, deposition means I try to deposit nano materials on top of a polymer and try to make a composite out of it. So, the electrodeposition, the schematic diagram of a different COOH twice architecture decorated carbon cloth produced using a 3 electrode system based electrodeposition method with diverse voltage scanning rates can be done. So, you have an electrolyte which is having a metal oxide precursor, you have a platinum is a neutral one. So, you have a platinum electrode wire which is there, then we have a reference which is a silver wire Ag/Ag silver chloride, and then you have a working electrode which is a carbon cloth, right. So, then this is a carbon cloth. So, if you try to scan it with different voltages, you try to get different nanoparticles which is getting embedded on a polymer matrix or on a cloth which can be used for applications. So, electrodeposition is a simple and a fast approaching to prepare nanocomposites using electrochemical reaction. This process involves electropolymerization of a polymer / a graphene composite from an aqueous precursor solution of a monomer, doping agent and a graphene oxide. So, you need to do electropolymerization, and polymerization process in presence of electrical energy, it is called as electropolymerization of what? Of a polymer / a polymer or a graphene mixed polymer graphene composite. So, this two is mixed from an aqueous precursor solution of a monomer, doping agent and graphene oxide, all these things are mixed together. Usually, the electrodeposition cell has 3 electrodes, one is called as the working electrode, one is called as the reference electrode, one is called as the counter electrode. Counter electrode is generally polymer, and the working electrode on which the layer is to be deposited, the reference electron is AgCl, whatever is there. So, the working electrode consists of an electrically conducting material or a substrate which is nothing but glassy carbon electrode. The electrodeposition of the polymer occurs at a specific potential and stops when an appropriate amount of charge has passed. So, you can also control the process. As a result, a nanocomposite film is formed on the surface of the conducting material, and if you stack all these things, you can try to make a thick layer of nanocomposites. So, if you look into the properties, mechanical property, the effect obtained is tensile enhancement and hardness, finds its application in automotive industry and textile industry. The chemical, highly reactive, catalysis and antibacterial, sites for functionalization, barrier properties, packing material, medical devices and smart textiles are coming up today. Smart textiles are textiles wherein which it tries to change the color. Then filtration membrane is also coming up. Physio and chemical, super hydrophobicity is talked about, self cleaning coatings are coming up today. So, if you want to make a shirt and if there is a stain, it gets cleaned of its own. That means to say basically it does not allow the particles to enter inside. Then thermal flame retarding is there. So, it is used as a protective coating in insulating panels. Optical, so refractive index and transmittant fluorescence, it is there. So, it is used for optical imaging lenses. So, if you look at a car, these are nowadays several parts of a car is now replaced by nanocomposite. Lightweight graphene based materials are used for structural applications in the engine. Graphene nanofibers are used for integrated sensors. Then functional textiles are used for detecting. The sensors for pollution detection and safety is also there. Smart adhesions are coming up today. So, wherein which it can expand and contract depending upon the temperature, and then you have nanofluids which are coming up for maintaining the thermal temperature, friction and thermal management which is done by nanofluids, and nanostructured thermal emissive materials which are used for thermal energy materials which are used for cooling and heat recovery are being considered. So that these are some of the applications where polymer nanocomposites are exhaustively used in automobile. So, some more examples: powertrain, timer belts, engine cover, inverter cover, coatings, headlamps, tires, and then interiors. All these things are made out of nanocomposites and they are finding its applications. So, polymer nanocomposites are finding out for environmental remedial measures, energy storage, electromagnetic shielding, sensing and actuation, the transportation and safety, defense systems, information and electronic industry are using it, OLED, LCD are using polymer nanocomposite, and novel catalysis are done for nanopigments are also coming up. These are the areas where polymer matrix nanocomposites are used in a very big way. In conclusion, many highly hyped technology products, polymer nanocomposites are coming up into the market. Polymer nanocomposites exhibits superior property in mechanical, thermal barrier, optical, etc. Owing to the polymer nanocomposites, how presence omnipresence in various fields of applications is seen. Polymer nanocomposites finds various applications could be synthesized by proper selection of matrix, nano reinforcement, synthetic method and the process. Surface modification is also very important. Many products based on polymer nanocomposites have been commercialized today. Therefore, we can conclude that various types of nanocomposites and their surface modification procedures, some unique properties of nanocomposites and its offer for various technology applications can be achieved. Thank you very much.